Okay, so good afternoon. So welcome to the class. I'm Kenjiro Taro, who is teaching this parallel and distributed programming course. I don't know, so can you hear me in the room? Okay. So I'm checking whether the remote folks can hear me. I think you can. So okay, so it's time to get started. So I'm teaching this parallel and distributed programming course, and this is the plan for today. So by the way, so in this year too, I'm going to do this class in the hybrid format. So you can either come to the classroom or you can join the Zoom. And because this is the first lecture after the summer vacation, I am slightly worrying about whether I am doing everything right for hybrid classes. So I'm checking what is seen by the remote folks by a separate smartphone and checking on the screen. But so doing hybrid classes, in many ways confusing. So if you think I'm doing anything very stupid, like speaking with microphone muted or start saying something without showing right things on the screen or Zoom screen sharing. So this may be happening at any time in this hybrid class. So with that said, so here's the plan for today. So after this, I'm going to give you some introduction or some brief talks raising your motivation. And one big thing for today is I like to make sure that during this today's lecture, everybody gets ready for doing exercises and assignment in the Jupyter environment I'm providing to you. So you just follow the instruction on this page. So I think you can do it by yourself after you get the right information, which is the password for this environment. Okay. So I'm hoping to give you some time to work on this Jupyter environment after having done this introductory part, which I'm hoping we'll finish in 40 minutes or something like that. But before I start, so this is a note for some of you. So if you haven't registered yourself in this ITCLMS course, please do so now. Because this, so I need to be able to see your name in this ITCLMS course page so that I can give you the password for the environment. So if you haven't registered yourself in the ITCLMS course, then you cannot get access to the Jupyter environment. So if you haven't registered yourself in the this course in the ITCLMS, so please do so now. Slightly confusing is that it is different from formally signing up for this course through UTAS. So even if you do it today in ITCLMS, if you haven't signed up in the UTAS, you still should do that later when you decide to do so. But so in other words, you don't have to worry that if you register yourself to the ITCLMS, it doesn't mean you formally signed up for the class. So it is a separate thing. So ITCLMS registration is necessary for you to work on Jupyter environment for today's exercise and assignment you do later today. Okay, so I hope that everybody can finish this getting ready for the environment in a matter of 10 minutes or something. So after that, I'm hoping to give another talk on OpenMP, and also hope that you have some time later in today's lecture, you have some time to work on the first real exercise, which by the way is going to be the first assignment you need to submit. Whose due will be about a month from now, and the details, I'm going to announce details later in ITC LMS. Okay, so with that, I'd like to get started with the introduction, but before we start, do you have any questions at this point? Okay, so the introduction. So you can see this slide by yourself by clicking this link. So by the way, yeah, like I said, the hybrid lecture is pretty confusing from the instructor's point of view, and what I'm showing now is many small windows. So I'm actually hoping that I can have a separate screen, so dual screen in this setting, but somehow I don't know how I can connect to this screen on the desk with the PC. So I'm resorting to screen mirroring. So what I'm seeing on my laptop is exactly what everybody is seeing on the classroom screen or Zoom screen sharing. So sorry about this messy stuff, Zoom chat and Zoom, I don't know, menu and everything. So it's pretty messy. Okay. Present as a slideshow. Does it make things better? I don't think so. Okay. So I think it's acceptable. So this is an introduction about this course, and I hope I'm able to motivate many of you. So the contents are the following. So why do you care about the parallel programming? And what parallel machines look like nowadays, and where these machines nowadays get the performance they claim they have. And then lastly, about how to program these machines anyways. So first, why parallel programming? So why do you want to learn parallel programming? So the fundamental fact that motivates you to learn parallel programming is that the processor frequencies no longer increase. So this is something called the end of Dennard scaling. So this is showing how processor frequencies evolve over time since 1970 up to 2015. Unfortunately, this database doesn't get updated with very recently, but the trend is very clear. So the trend is that up to the early 2000, the processor frequency was rapidly increasing. So literally in the exponential rate. But after 2000, early 2000, somewhere like 2005, they no longer increase almost at all. So when I was a student, which was somewhere like early 1990, so I still clearly remember that a desktop workstation on top of my desk had a frequency like 25 megahertz. And after one generation, it almost surely at least doubled. So it took a long time until we get the first processor having the frequency of, for example, 1 gigahertz. But after that, they no longer increase. So there's a physics and very technical reason why this is the case. So it's not that it's not just about the, for example, marketing frequency or some arbitrary choices made by the processor designers. So there's a reason why you no longer want to do this or you cannot do this. So I cannot get too much into the reason why this is the case. But well, like I said, there's a technical reason behind this. So one thing, this is one thing. And the another factor is that there used to be, well, so there are currently too, many architecture design techniques to increase performance of ordinary serial programs by extracting very fine-grained parallelism, something called instruction level parallelism. But these techniques, so beyond some levels, beyond some threshold, these techniques are less likely to pay off. So it is getting increasingly more difficult to pay off. By the way, I had a chat. There are two course pages on LMS and both have the same course ID, it seems, for information communication engineering. I'm not sure which to choose. I don't think it matters. So you can choose either one, but just to be safe. So I'm just thinking that this one is the main course. So 4840,004. So I don't think it matters, but so you can register either way, but just in case. Okay. Sorry. So where was I? So there used to be techniques for increasing the performance of serial programs. So I talked about the instruction level parallelism. So the kind of parallelism I'm talking about is something like, for example, in ordinary serial programs, you have an expression like ax plus by. And while you are doing a multiplied by x, well, actually you can do at the same time the b multiplied by y because there are no dependencies between them. They are independent. So the processor, recent processors are very good at automatically exploiting this kind of very fine-grained parallelism that exists inside a small expression or small groups. But you can easily imagine that you cannot you cannot extract many parallelism in this way. So we are talking about serial programs. So all you can find in serial programs are very a small amount of parallelism, like when you have a fairly large expression, ax plus by plus cz or something like that. But you cannot, for example, extract 1,000 individual instructions you can execute in parallel. So for these two reasons, so processor designers had to resort to techniques which are less, in a way, automatic. So processor designers used to try increase the performance of ordinary serial programs by increasing frequencies or increasing instruction level parallelism. So that can be extracted automatically by the processor. But these two things are getting increasingly more and more difficult. So recent trends such as multi-core processors, many core processors, and GPUs are all in part response to it. So in other words, so when you have more transistors, for what kind of purposes these bus transistors should be profitably used. So it used to be the case that you can profitably use these for increasing instruction level price, but it is getting more and more difficult. So we simply have more cores and expose to the programmer the fact that you have many cores, and to get good performance on this processor, you need to have parallelism in your software. So more explicitly than very fine-grained instruction level parallelism like AX plus BY. So this is what is happening. So in other words, there are no such thing as serial CPUs anymore. So virtually all CPUs nowadays are multi-core processors. And there are even so-called high-performance accelerators such as GPUs or Xeon Phi. Maybe people do not consider Xeon Phi accelerators anymore, but well, so they are actually designed on the same principle as GPUs. So these processors, so generally considered as high-performance processors, run at even lower frequency than ordinary processors. So in other words, these processors do not try hard to get serial programs faster. So they are trying to get parallel programs faster at the cost of perhaps slower serial performance. So you may think that this is the case only for ordinary popular off-the-shelf commercial processors. But actually, this is not the case. So you may think that, okay, so if you look at the very high performance, high-end processors, perhaps used for supercomputing, the situation may be different. But actually, this is no different. So this is a list of the fastest 6 processors. Actually, there's a list called the top 500 listing the fastest 500 supercomputers in the world. So as I'm just showing the top 6 of the list. And each of these machines has quite, in a way, ordinary either GPU or CPU as a component. So there's nothing special in these so-called supercomputers. So this one has an AMD GPU. So this one has a, this is a Fugaku, so it's CPU, but it's running merely at 2.2 gigahertz. So which is quite ordinary. So it is actually as almost the same as the laptop CPUs. So another AMD GPUs. So one interesting thing is that they are somehow AMD, not NVIDIA. And we have 2 NVIDIA supercomputers. And another many core processor designed by China. But this processor has 260 cores, each running at merely 1.45 gigahertz. So no processors have remarkably higher frequency than what we usually have in, for example, laptops or servers. So the only thing actually quite different in supercomputers is simply the number of cores they have. So again, in supercomputers, the way they get performance is the ample parallelism, not for example, extremely fast processor frequency. Well, actually, so supercomputer situations have been like this for a number of years. So one thing that is very remarkable recently is that this trend is in a way the same for our ordinary machines, ordinary servers, or even laptops. So here's the simple implication to the software. So existing software, serial software, do not get faster, at least not dramatically faster on new CPUs. So you may have known this as a matter of fact for a long time, but well, one thing that I need to emphasize is that actually this was the case when I was very young. So you don't modify the software at all. You get a new generation of processor, but the software automatically gets faster because it has a higher frequency. But this doesn't happen anymore. So just writing a software in, for example, C or C++, takes you nowhere close to the machine's potential performance. So unless you know how to exploit parallelism of the machine. So this is the fact of life in today. So you need to understand, does this program use, for example, multiple cores? And if so, how the work is distributed across these cores? And I come to that later, but another important dimension is that the software use something called SIMD instructions. Does it exploit SIMD level parallelism? Also, does it have a good instruction level parallelism, which is still important, especially on CPUs. Not so important in GPUs, actually. So let me show you some simple example, which I hope motivate you to run parallel programming. So this is a very common matrix multiplication code that is simply written in C. So nothing nothing special is done to get great performance. So there's no surprise actually that this piece of software performs very poorly. But on the other hand, so this piece of code doesn't do anything obviously redundant or obviously stupid. So, well, actually, it used to be the case. So it's long ago, but it used to be the case. C++ code written something like this is getting somewhere close to the peak performance. But what kind of performance does it get in today's processors? So this is a simple demonstration. So this is actually a machine you're going to use for exercises. And here we have matrix multiplication code that looks like what I have just shown in the slide. So the simple one is something like this. So this is, well, so there's some template, mysterious template stuff, but otherwise it is almost identical to what I have just shown in this slide. And this is what you get in this simply written C or C++ programs. So it is doing the matrix multiplication where A is 8,000 by 7,000. I'm sorry. So actually A is 8,000 by 240, and B is 240 by 7,000, and C is 8,000 by 7,000. And this is the performance you get. So I come to how you interpret this number later, but it's something like 0.5 clocks per CPU clock. And so, yeah, so as you witnessed, it's obviously taking, very long time. And the number of seconds it actually took is So it is shown here. So it's this nanosecond, so something like 16 seconds, right? For this matrix multiplication to get done. And just for the comparison, this is another. I'm sorry. The implementation that takes advantage of first of all SIMD. So I come to that later. Instruction level parallelism and OpenB. So for the multi-core parallelism, and yeah, it is finished almost instantly, and you get something like 500 flops per CPU clock. And actually, this is actually now very close to the peak performance, and so the matrix, so the matrix size was actually too small to get decent performance. So I'm just making the amount of computation larger by having a command line parameter. So, and then you get something like 2,000 floating point operations per CPU clock. And if you do the same amount of computation with the simple software I have just, the simple implementation I have just shown, it literally takes forever. So it's repeating the same computation 14 times. So the single iteration took something like 16 seconds. So it's going to take, well, more than 3 minutes. So 3 minutes versus something like this. So on exactly the same machine. Right? So this is the difference I'm talking about. So I hope you are somewhat motivated. So by just writing the software in more efficient way, you can get literally more than 1,000 times the speed up. So the next topic is what this machine actually looks like and where the performance comes from, for what you need to exploit to get decent performance. So this is what a single machine or something called a node actually looks like. So imagine you have a server box and you open the box. So you will see something like this. So this is something called a motherboard. Depending on the type of the machines, you have one or a couple of what is called a socket. So this particular motherboard has 4 sockets, each being capable of plugging a CPU. So you get a CPU on each socket, CPU socket. And inside each socket, you have multiple, something called a cores. And more precisely, it is often called a physical core. So in this particular picture, you have 6 physical cores in each CPU chip. And very similar to the concept of physical core is something called a virtual core. So the organization is, so each physical core may have multiple, so typically 2 or 4, something called a virtual cores. So the difference between the virtual core and the physical core is not so different, at least from the software's perspective. So from ordinary software perspective, they are almost the same. Each virtual core is able to fetch an instruction at each cycle. So from the operating systems or virtually any sort of software point of view, this particular machine looks like it's having 12 multiplied by 4, 48 processors. So each capable of fetching an instruction at every single cycle. And more importantly, so in each core, you have another level of parallelism called SIMD, or that stands for single instruction, multiple data. So, okay, so I got a question. So what is the advantage of having a virtual cores? Can two virtual cores operate at the same CPU time for physical core? So the advantage is that, so if you have a piece of software in which a single thread cannot exploit all the resources of a single physical core. So by the way, so I forgot to mention that. So the what are shared among virtual cores, multiple virtual cores within a single physical core are, for example, floating point execution units, so arithmetic units and load and store units. So all these execution units are typically shared between multiple virtual cores within a single physical core. So the situation in which having multiple virtual cores is advantageous is that a single thread cannot utilize all these resources. So somehow, for some reason, a single thread cannot, for example, execute as many floating point instructions as supported by the physical core. Then chances are that when you have two virtual cores at the same time on the physical core, you may be able to get close to peak performance. Did I answer your question? Okay. So by the way, this is very similar to how the GPU programs get performance. So well, I come to that later. So I don't get into too much into it for now. So I was speaking about this SIMD. So SIMD is another level of parallelism within each single core. So basically, it is an instruction that can operate on many operands with a single instruction. So what you have in each core is a number of something called SIMD registers. And each SIMD register can hold many values. For example, 8 double precision floating point numbers or 16 single precision floating point numbers. And these SIMD instructions will operate on SIMD registers. For example, you have an add instruction that adds 2 SIMD registers, which in effect can add, for example, 8 double precision floating point numbers or 16 single precision floating point numbers with a single instruction. So this is SIMD. And finally, you have a single core that can execute multiple instructions in every single cycle. Like I said, this is something called instruction level parallelism or ILP. So you can notice that there are multiple levels of parallelism. So you have a motherboard on top of the hierarchy. And you have, for example, in this particular case, 4 sockets, 4 CPU chips. Each CPU has as many as, for example, 64 cores or even more nowadays. So in this picture, I said 16, but nowadays it's more. And each core may have a couple of virtual cores, and each core has SIMD parallelism and instruction level parallelism. So they are all combined to get close to peak performance. So like I suggested already, so the performance comes from multiplying these parallelisms at all levels. So this is the degree of parallelism per CPU. So it is the width of a SIMD. So for example, if a single SIMD instruction can operate on 8 floating point numbers, it is 8. And you have instruction level parallelism, which says this is the number of instructions this CPU is capable of performing every single cycle. And it is multiplied by the number of cores. So when you talk about the peak performance or the performance of the processors, we often talk about peak flops or the floating point operations per second. So if this is the number you are interested in, so it is typically calculated like this. So the SIMD width, the number of floating point numbers a single SIMD instruction can operate on, multiplied by 2. Well, so I'll explain why this, where this 2 comes from later. And typically, peak flops or nearly peak performance are attained by using lots of something called FMA instructions, which stands for fused multiply add instruction. So it is a single instruction that can do both multiplication and addition with a single instruction. And many processors are optimized for doing as many FMA instructions as possible per cycle. So the peak performance is often attained when you are using lots of fused multiply add instructions. So the reason why you have 2 here is that a single fused multiply add operation actually performs 2 floating point operations. So 1 addition and 1 multiplication. And we are counting the number of floating point operations per second. So this is the number of flops a single FMA instructions is capable of performing, right? And this is the number of FMA instructions a single core can perform at every single cycle. So you multiply this by the processor frequency to translate it into the number of floating point operations per second. And finally, you multiply this number by the number of cores to count the performance of a single CPU. So I plug actual numbers in I guess the next slide or 2. But before getting into this, so I'll talk a little bit about GPUs too. So you may think that every time I click this, somehow the slide advances, which is very annoying. So you may think that the GPUs and CPUs are very different processors. But actually, I like to emphasize commonalities between them than the difference between them. So this is what a typical GPU looks like nowadays. So a single GPU device consists of many what NVIDIA calls streaming multiprocessors. So, but it is actually quite similar to the concept of physical cores in CPUs. What's slightly different, but still similar, is that each streaming multiprocessor is highly multi-threaded. So this is conceptually very similar to the difference between a physical core and the virtual cores I just mentioned and somebody asked. So streaming multiprocessor is like a physical core, but this single physical core can execute multiple threads, can take instructions from multiple threads. So for example, it can take instructions from this thread at a single cycle, and the very next cycle, you can take another instruction from another thread. So each streaming multiprocessor is very highly multi-threaded. And it can execute in the unit of something called warps. So this is again another NVIDIA terminology. And each warp actually consists of 32 what they call CUDA threads. So in a single cycle, streaming multiprocessor works by determining warp that it executes in this particular cycle and executes all these 32 CUDA threads at the same cycle. So actually, this is somewhat similar to SIMD instructions of the CPU, which can operate on multiple operands, but need to do exactly the same instruction. But actually, this is the case for warp in NVIDIA GPUs too. So all these 32 threads should do exactly the same instruction. Otherwise, they take multiple cycles to execute. So this is what I'm hoping is a very useful comparison between the GPU and CPU. So I think streaming multiprocessor is just like a physical core of a CPU. And you have many threads concurrently running on a single streaming multiprocessor. And it is fairly analogous to simultaneous multithreading or the virtual core I just mentioned in earlier slide. So exactly the same thing. And you have a group of 32 CUDA threads, which is called a warp. So this is the unit of issuing an instruction in GPU. So all these 32 threads, so for them to run really concurrently, all these 32 CUDA threads need to do exactly the same instruction. So this is how the GPU get a performance. And this is very analogous to SIMD instructions. And on CPU, you have multiple instructions simultaneously executable from a single thread. So this is something the GPU is actually lacking. But yeah, they are in many ways different. It's very similar. And here's some actual numbers. So in terms of the amount of parallelism you have at each level. So for example, so I'm just showing generations of Intel CPUs. And the latest is something called Ice Lake. And the width of the SIMD is something like 16 for single precision floating point numbers, or 8 double precision floating point numbers. So because single precision floating point numbers is 32 bit. So 32 multiplied by 16. So it has 512 bits in a single SIMD register. And each of these CPU is capable of executing up to 2 FMA instructions per cycle, per core. So actually, the peak performance is attained when you execute or complete 2 FMA instructions at every single cycle. And you have frequencies like 2.0 to 2.6 or 2.4. And the number of cores is something like 38 nowadays. So you simply multiply all these things to get so-called peak performance of this processor, which is something like 6 teraflops for single precision numbers and 3 teraflops for double precision numbers. And this is a number for NVIDIA GPUs. So something analogous to this SIMD is, like I said, a warp. So which is essentially, well, so in some way, it's essentially 32-way SIMD mechanism. And each streaming multiprocessor can execute up to 2 warps in every single cycle. So what it is capable of doing is pick up 2 warps, which is 64 CUDA threads. each doing a single FMA instruction. And the frequency is something like this. And the number of streaming multiprocessor is 108. So by multiplying all of these, you get something like 19 teraflops or 10 teraflops, depending on you're talking about single precision or double precision. So this is just the same calculation to derive these numbers. So if you do actually do this calculation by pencils or Python, you exactly get this. And this is what processor vendors advertise as their peak performance. So what I'm trying to emphasize here is that, so first of all, the way they get this performance is not very different between CPUs and GPUs. So both have something like SIMDs, both heavily rely on FMA instructions, and they are both trying to execute something like two SIMDized FMA instructions every single cycle. And they both get so many cores or streaming multiprocessors, depending on whether you are CPU or GPU. So the question I got is, so why the frequency of GPU is smaller than CPU? So yeah, this is in a way the design choice. So if you increase the processor frequency, you certainly need to burn more energy. And by burning more energy, it's getting more difficult to get a more parallelism, say in terms of, for example, the number of streaming multiprocessors. So there's no fundamental reason why this has to be the case. So of course, you can think of designing something like a more like a GPU, which has higher frequency. But yeah, this is, I guess, the number that strikes the balance between power consumption and the performance. Okay. So by the way, so you may know there's something else to the recent GPUs, something called the tensor cores. So I don't get too much into it, but it's essentially a special purpose instructions for small matrix multiplication. To be specific, A is 4x4 matrix, B a 4x8 matrix, and C 4x4 matrix. So by having this special instruction and the processor highly optimized for doing this instruction almost every single cycle, you can get very different peak performance. So if you count the performance that comes from using this tensor core special instruction, you get something like 156 teraflops. So which is an order of magnitude higher than what you get solely with FM instruction. So I guess the important takeaway of this is, so this is not very general purpose. So FMA is already to some extent not very general purpose, but still it's very versatile or flexible. But this special purpose matrix multiply instruction can only be used for only for, let's say, deep learning. And so they claim that the operand is 32-bit, but actually they are not genuine single precision floating point numbers. This is what they call TF32, which uses only 90 bits out of a 32-bit number. So yeah, so it's certainly useful for accelerating deep learning, which is doing lots of matrix multiplication. But you can easily imagine that the situation in which you can profitably use these instructions is not very large, at least compared to general FMA. So the basic trends or the main takeaway is that processors' performance improvement is getting less and less generic, transparent, or automatic over time. So it used to be very generic and transparent in the sense that in new generation of CPUs, you get higher frequency and you get a higher instruction level parallelism, or so-called out of order, better out of order execution units or better superscale processors. So we used to enjoy the performance improvement, this transparent performance improvement by the processor. But over time, the time has come in which we need to take advantage of explicit parallelism you can expose in your software. And more recently, the advertised performance of the processor, or especially GPUs, is increasingly relying on special execution unit or the special instructions such as matrix multiplication. So in short, the performance is getting more and more dependent on how you program. So let's talk about how you program the machine. So no matter how you program it, so you need to maximally utilize all levels of parallelism I have just talked about. So instruction level parallelism, SIMD, multi-cores. How exactly depends on the underlying devices and the level of abstractions of the programming language you chose. So like I said, so recent processors are all multi-cores or GPUs. So no matter whether it's CPUs or GPUs, you need to explicitly exploit a parallelism. But how this is done from the software's perspective may not be so obvious. For example, we can still imagine a so-called ideal world in which, although the processors are very complicated and the processors need to be able to need to be programmed for parallelism in mind, the actual programming language you use nicely hides all these details. So you still program just like ordinary programs, so in very high level terms, and everything else is done just by the compiler or the language processors. So if the actual world is as good as what I just described, then probably there's not much point in learning how you actually program these machines. But the actual real world we are facing today is in a way far from the ideal world. So you need to very explicitly program many low-level details. So this is in a way the fact of the life, at least for today. So that's why parallel programming is still a subject for much research. But with that said, so there are many ways and these parallelism can be exposed to the actual programmers. And I'm just listing many possibilities. So on CPUs, on the very lowest level, you could have operating system level threads. And for GPUs, the lowest level machinery is something called the CUDA threads. And there are some programming languages based on something called SPMD, a single program multiple data paradigm. So this is the programming model in which the entire program runs with the fixed number of threads. So this is a fairly straightforward abstractions of today's multi-core processors. For example, when you have 64 physical cores, you simply say, okay, so you have 64 threads running, all running the main program of your program, main function of your program. And you cannot do anything else. So you do everything with all these fixed number of threads. So it is pretty inconvenient. So still very low level. So much more convenient is some programming construct dedicated for loops. So as you already probably know, so typically the program spends most of the time in some loops. So not surprisingly, many parallel programming languages have some nice support for parallelizing loops. And another very useful paradigm is something called tasks. So you can dynamically create tasks during the course of execution. All these tasks, dynamically created tasks are automatically distributed across cores. And there are in some cases in which you can simply rely on libraries that are internally parallelized. So you simply call it from within your sequential program, and all the details of parallelization and SIMD and everything is nicely hidden in the library. So this is especially true for very common operations that appear in matrix of computation, such as matrix multiplication. So skip this. So there's a similar story about how you program SIMD. So again, in an ideal world, you simply, for example, write a ordinary loop, and exploiting SIMD instructions is just done by the compiler. So this is what we imagine as an ideal world. But again, the real world is not close to this ideal world. So in the worst case, you need to resort to writing an assembly, but somewhat better than assembly, but still you still can do almost everything you should be able to do on the CPU is something called intrinsics. So it is superficially it is not assembly. So you are programming in C programming, and just calling some unfamiliar functions to access these SIMD instructions. And there are some other ways. So I'll get to this when appropriate. So this is another thing you are exposed to in this course. So to wrap up, so this lecture is for those of you who want to have a first-hand experiences in parallel and high performance programming. So not just for doing things in parallel. So much more about how you get actual performance. So either using OpenMP, CUDA, or SIMD programming. And another thing I wanna expose you to is something called task parallelism for divide and conquer algorithms. So this is essentially about good tools to solve otherwise very complex problems to solve. So this is another thing I want to expose you to. And yeah, like I already repeated several times, the one subject is to understand when you can get very close to peak performance, whether it's CPU or GPU. and how you actually get it, how you actually get it in your programs. And yeah, throughout the course, you wanna learn, you are going to learn many reasons why you don't get a good parallel performance when you thought you would. And another thing is to have a good understanding about caches and memory and why they matter so much for performance. All right, so I have maybe spent more time than I initially anticipated. So, okay, that's about it for the introduction. So is there any question up to this point? Okay, so let's have a let's have time to work on the assignment, not necessarily on the assignment. So just to get ready for the Jupyter environment, so that you can start working on the exercise when the time is right. So for that, basically, so you go to the ITCLMS and you get the first assignment, and you should be able to see the comments from the instructor. And this comments from the instructor tells you what is your password and what is your username on the Jupyter environment. And with that information, you should be able to simply go to this page and you do everything by yourself. So basically, you just visit this page and you enter your username and password you get from ITCLMS. So, okay, so let's have 10 minutes or something to get everybody on the same page. So to make sure that everybody can access this environment. So is there any of you who have just registered yourself right before the lecture begins? So in which case you do not have the password yet. So let me check. Okay, so yeah, so there's one of you. Okay, so you just registered. Okay, so I will work on this now, and so wait for a few minutes. Okay, so there are a couple of you who appear to have just registered before the lecture. Okay, so there's plenty of you. So I work on that. So yes, I should turn off the screen sharing just so that I don't reveal any secret information. And also, I guess I need to turn off the external screen. Also, yes, so wait for a sec. I feel have just registered before the lecture. So I thought I have just done that. So I actually have done that for most of you, but when I checked the ATCLMS again, there are another of you who have just registered. So I guess except for a couple of you, all of you who should have gotten the password. So I am working on the two of you who have just registered again. I think I have done that for all of you. So I'm sharing the screen again. So I got two questions. One is, so is there any rules used when using the machine? Like, can we install any package we want? So you are ordinary user. You are not, you do not have a root access or supervisor privilege. So for example, you cannot install any software that needs a supervisor privilege. So Otherwise, you can do whatever you want to do. Did I answer to your question? Okay. So the other question was, how do you check the attendance in this class? So for today, I didn't. Probably I won't throughout the course. But there are sometimes in which I expect you to come. Like for example, in this week we do the we work on the exercise during the lecture, and you are supposed to do your work during the lecture. And so in these occasions, I may check not necessarily the attendance, but what whether you do what you're supposed to do during the lecture. Okay. So let's do this until 10. So 6:10. After which I'll get back to slides talking about OpenP. But I guess I'm hoping that this is pretty straightforward. So up to a point when you can see something like this, please get it done in 5 minutes or so. And if you have already done this, you can actually go ahead to another notebook I have just given. So which is so display. So desktop is so messy. So you should. So let me show it. So you should be able to see something like this, and you should able to get these two notebooks. And the first one is fairly trivial. So just talking about how you work in Jupyter Notebook in general. So basically, what the only thing you need to master is Shift plus Enter. So just enter while you're pressing Shift. And this is the first real thing talking about OpenP. So if you have done everything else, yeah, you can just immediately start working on this. Yeah, of course, I didn't explain OpenP at all, but so the another question. So is there a deadline for the PD01 MP assignment? Yes. So I haven't decided yet, but my plan is this one is due about a month from now. So like early November or something like that. So many problems are actually very straightforward, or almost adding a few lines and yeah, you are done. And there's a couple of problems that you need to spend some time on. Okay, so let's get back to the slides. So maybe I should keep the slide in this way so that Zoom stuff does not annoy me. So this is yeah, about OpenMP. So the slide has so many it has so many slides. So I hope I will finish earlier, just after the very brief introduction, so that you have some time working on the Jupyter notebook during this class. So I'm hoping to finishing, well, not of course all the slides, but a very early part of the OpenMP thing in a short amount of time. So before getting into the OpenMP itself, so let me briefly explain a small running example I'm going to use throughout this introduction, which is sparse matrix vector multiply called SPMV. So sparse matrix is a matrix whose elements are mostly zeros, like this. So each dot represents a non-zero element. So the sparse matrix, in terms of the definition, it is a matrix whose number of non-zero elements, often denoted as n and z, is much smaller than the number of all elements, which is m by n. M is the number of rows and n the number of columns. So sparse matrices appear everywhere in applications. So I don't get too much into it, but so for example, in scientific simulations, you have meshes, and especially in the case of irregular meshes like triangular meshes, you have a sparse matrix. So the ij element of the sparse matrix is some weight depending on the application. So some weights connecting nodes I and j in the mesh. You also often use sparse matrix to represent graphs. So graphs, of course, appear in many applications. And so in the sparse matrix representation of a graph, Aij is typically the weight associated with the edge from I to j, node I to j. So there's so many things that can be naturally represented as a graph. So web pages, social networks, so connections between people, low traffic networks, connections between cross points, crossroads, so metabolic pathways and things like that. So many problems, not surprisingly, can be solved using SPMV, so sparse matrix vector multiplications. So eigenvalues and whose applications, for example, include page rank computations and graph partition. And of course, partial differential equations use this SPMV all the time. So sparse matrix is somewhat different from ordinary dense matrix. So the number of non-zero elements are so small that represent it straightforwardly as the n by n two-dimensional array is very wasteful. So in many cases, just impossible for real applications you care about. So in order to represent a sparse matrix, you typically use a data structure that takes memory or associated computation only for non-zero elements. So which leads us to several representations such as a coordinate list or complex sparse row, etc. So this is a coordinate list, which is simplest conceptually. So it simply represents a matrix as a list of or array of triples ij and the value a ij. So when you have a non-zero element here, then you simply have a number indicating which row is it in, which column it is in, and the actual value. So this is the entire data format description in terms of the C struct. So you have number of rows, number of columns, and the number of n and z, non-zero elements. And each, so you have the pointer to elements, or conceptually the array of elements, each of which has I, J, and Aij. So when in this representation, SPMV can be represented as something like this. So basically, you simply scan all the non-zero elements. So for each non-zero element, you get Ij and the value Aij. And then you simply accumulate Aij multiplied by the corresponding X element in order to perform Y equal Ax. So you multiply the matrix element and the vector X element and accumulate it into the corresponding the element of Y. Slightly different is something called compressed sparse law representation. So it's very similar to coordinate list. Actually, it puts elements of a single row in a contiguous range of elements array. And you have another array specifying which section of the elements array represents a particular row. So the actual data format description is quite similar. Sorry, this is not a COO. So this should be CSR. So like before, you have number of elements, number of columns, and number of non-zero elements. But each element simply has only J and Aij. So which row it is in, it is implicit so implicitly represents by where this element is in this elements array. So you have a separate array indicating where each row starts in this elements array. So in particular, so the row start ith element of elements to row start I plus 1 elements. So excluding this very element. So the one element before this one are the elements of the ith row. So this is how you represent sparse matrix using CSR. So in this CSR representation, sparse matrix vector multiplication can be written like this. So you have an outer loop iterating over all rows. And for each row, you simply scan the corresponding section of elements array using this row start array to know where does the ith row begins and where does it end. The actual body is quite similar. So you simply get J and Aij, the value Aij, and you do exactly the same thing for X and Y. So maybe, yeah, so far this has nothing to do with OpenP itself, but so to keep something like this in mind when I talk about some particular constructs of the OpenP, how this can be applied to this kind of computation. So OpenP, so it is by far the most popular and de facto standard model for programming multi-core machines, shared memory machines. But actually, more recently, it has a support for GPUs. So it is getting sort of more universal than before. So it is designed as an extension to C, C++, and Fortran. And that the way it extends C, C++, Fortran is by something called the directives, plus some APIs, functions. And this directive is given by something called a pragma in C or C++. And in Fortran, it is given by some comments of the particular format. And there are many both free and vendor-supplied compilers. So virtually any C compiler or C++ compiler nowadays supports OpenMP to a different extent. So here's the reference to OpenMP. So the spec is growing bigger and bigger over time and over versions. So you don't want to read all of them from beginning to the end. So I talk about some very important elements of this OpenMP in this lecture. But at times you want to see yourself the spec itself. So these are pointers you may want to visit later. And so here's how you actually compile OpenMP programs for multi-cores. So this is actually somewhat dependent on the compiler. So in the case of GCC or LLVM, whose command names are Clang or Clang++, depending on whether it's C or C++. So in these two compilers, you simply give this -f OpenMP option in the command line. So something like this. Of course, it is, well, after you write some OpenMP programs, which I didn't talk about at all, but after you get some OpenMP programs, you compile them by giving -f OpenMP. In the case of NVIDIA HPC SDK, which also supports OpenMP, whose command names are either NVC or NVC++, depending on whether it's C or C++. So in this case, you give -mp option to the command line. And in this lecture, we are going to use LLVM compiler, so Clang or Clang++, and NVIDIA HPC SDK. The primary reason being that they actually both support OpenMP for multi-core and GPUs. So you can do GPU programming with OpenMP, which is very good things to have. They also support somewhat low-level CUDA interface for GPU programming. So both, are very great at extending support for a GPU program. So that's why I picked these two compilers for this lecture. So once you get OpenMP executable compiled either with -f OpenMP or -mp, you run the executable by giving this environment variable, which specifies the number of threads, basically. So the same OpenMP program can run with any number of threads. And when this OMP num-thread is unspecified, it uses a number of available processors, basically all the cores, so all the virtual cores. So whatever visible to the operating system as a processor. So this typically includes the virtual cores. So it may be more than the number of physical cores you actually have. And you can see this section of the OpenMP spec for details. So there's some other rules that determine the number of threads. And a few more things. So actually, there are two pragmas you must learn first to do anything useful with OpenMP, which one is pragma OMP parallel, which is to launch a team of threads, so just like this, so these 4 threads. The other is pragma OMP4, to distribute iterations of a for loop into these threads. So they are typically used in combination, but in terms of the language spec, these need to be understood separately. So it's better to explain them separately. By the way, so all OpenMP pragmas have this common format. So they all begin with hash pragma OMP. So what you actually need to remember for each construct is something that comes after pragma OMP. So this is what the OMP parallel does. So the basic syntax is you have hash pragma OMP parallel followed by a statement, C or C++ statement. The semantics is that, this statement before OMP parallel is supposed to be executed by a single thread. So like this. So this guy executing this part. And when it encounters this hash pragma OMP parallel, it creates a team of threads whose number is determined by OMP num threads and something else depending on how you exactly specify it. So I didn't get it into it. So basically, so whatever number of threads you specified using this OMP num threads. And the current thread becomes something called the master of this team of 4 threads in this particular example. And somewhat importantly, sometimes confusing, is that this statement S gets executed by each of these team, each of these threads in the team. Okay, so this is not itself a construct for doing something in parallel, in the sense that you distribute the big amount of work into many underlying threads. So this is just for creating threads, each executing this same statement. And after the master is done with this statement S, it waits for all other threads to finish this statement S, and then continue. So just to give you an example, this is just stupid example in which you give this OMP parallel just above this printf word statement. So when you compile this and execute this with the number of threads is being 1, then both hello and word is printed once. Okay, so I actually by should be printed too. So it's just my type. On the other hand, when you have OMP num threads being 4, then this statement is executed by each of the 4 threads you just created by this OMP parallel. So this is how this happens. Okay. I'm running out of time. So rather than spending all the time just talking about through the middle of the slide, let's just have some time to do some work in this PD01 Jupyter notebook in the remaining time. So so we only have 5 minutes, but let's do this anyways. And meanwhile, you can ask questions or just let me know whatever troubles you encounter. Okay, so I got a question asking, what you were supposed to write here, student ID. So, well, actually, it's not that important, but yeah, I suppose it be your yeah ordinary student ID, not a Utopia account. Okay, so I just hope that in this during this lecture, so until the end of this lecture, everybody gets to a point where you can at least compile a OpenMP program and executed it with different number of threads like this. So essentially up to the program one. So I guess it's yeah, almost the time, and I think we are done for today unless you have any question. So any question? So if you have any technical issues, I'll be yeah in the Zoom for a while, so you may ask after the class. So I guess yeah, I guess we are done for today. So yeah, remote folks can leave the Zoom. Thank you. So the question, so do you have to press the validate button? So no. So well, actually the validate button is almost irrelevant. So I'm not at least using it at all. So just ignore the validate button. Yes. Thank you. Okay, so the other question is, can, can, uh, can you just submit directly after you completed all programs in PD01, this notebook? So the exact way you are supposed to submit this assignment will be announced later. Well, actually, it's going to be um, through Jupyter Notebook submission button plus some brief notes to ITC elements. So details will be described later, but stay tuned. Okay. So another question: how many assignments do we work on work on in this lecture in total? So well, it depends actually how we go, but in the last time, I think it was just a couple of times, 3 times or something like that. So I haven't decided it yet for this year, but yeah, I think it's gonna be something like that. 3 or yeah, 3 short assignments plus the final assignment, something like that. And another thing I have just written but forgot to mention is there's a Slack channel, so named 2020 this in this workspace. So how you exactly join this channel can be found here. So you can ask any question at any time on the Slack, emails, or LMS. So I'm just briefly explaining the trade-off of yeah reliability versus latency. So depending on your circumstances, yeah, choose whatever you think is best for the situation. All right, so maybe it's time to close Zoom. So if you have any other question and you want me to stay in the Zoom for a while, let me know. So otherwise, I am going to close this Zoom in a matter of minutes. Okay, so I think there are no more questions. I'm going to end the meeting. See you guys.